Hello and welcome to the student revision tutorials. This is Unit 3 Further Maths with TI-Nspire, and today's topic is recurrence models for geometric growth and decay. My name is David Tynan. Okay, so to today's topic, recurrence models for geometric growth and decay. It's the second webinar. The first webinar focused on linear growth and decay, or recurrence models for linear growth and decay. Today we're going to go through 5 problems. These 5 problems are also included in a tutorial sheet that would have been sent to all people who registered for this webinar. And during this webinar we will work through each of those problems in turn. You might have had a chance to have a go at them yourself. So let's see how we get on. So the first problem is describing geometric growth. So a particular tree species is known to grow at a rate of approximately 12.5% of its current height each year, and the tree is 100 centimetres tall when planted. So first of all, describe the growth of this tree as a geometric recurrence relation. Express the recurrence relation as a direct rule for calculating the height after n years. And then assuming this model works or continues to work to explain the growth, how tall will the tree be after 5 years? And I notice that you've got a little poll on the side to answer that. So if you haven't already, you could have a crack at that. And the final question is, how long will it take the tree to triple its height? Let's switch over to the calculator, and I should mention now that this file, which has quite a lot of material in it, will be available in the same folder that you accessed the file if you registered for the previous webinar. Okay, more of this later. Because of the amount of material I've got to get through, you'll notice that I've pre-entered quite a bit of material, and I'll talk to that rather than spend too much time typing things in. So I hope that's okay. So to the problem. The tree starts life at 100 centimetres tall. Well, it didn't start life, but it starts being planted at 100 centimetres tall. And the recursion is to say, well, if it's increased by 12%, then that 100 centimetres will be multiplied by 1 plus 12.5%. And that's written in brackets here as 1 plus 12.5 over 100 times that 100 centimetres. So if you like, this is the multiplier, which works out to be 1.125, but I've kept it in fractional form in this case. So if you do 1 plus 12.5 over 100 times the previous answer, you will now know, if you're doing this module, that you can just type in ANS and it will complete the recursion. That is, that it will always do 1.125 times the previous answer. So rather than go through that in great depth, I think people will be pretty good with that by now. We'll go to the idea of writing this recursion rule. So clearly there's a multiplier of 1.125, and so we could say that the next term is always 1.125 times the previous term, or the current term if you like. And the starting value, the V0, is 100. And we'll return to that way of describing it in a couple of minutes. A later question asks you to work out what will be the height after 5 years. So you'll notice here that you can just say, well, I want this multiplier, the 1.125 or 1 plus 12.5 over 100, to be raised to the power of 5, the 5 recursions if you like, times the original value or the V0 value. And so you can check your answer now in the multiple choice. If you haven't already, it should have reached a height of about 180 centimetres. And then the final question in here is to say, well, okay, how long will it take to triple its height? So that is, how long will it take for it to reach a height of 300 centimetres from its original 100 centimetres? And by now, I think you've probably done enough of these to know that you can use a solve command. So solve, when is the Vn, this is the direct rule, equal to R, big R if you like, to the power of n, multiplied by V0, which is 100 in this case. And we can see that it will take about 9.3 years. Okay, so that's sort of an introduction to the idea of a geometric growth, where there is a multiplying factor, as opposed to the earlier linear stuff that was done where it's an additive change. Okay, so just to round this problem off, here is the same problem context approached via a notes template. So this notes template allows you to enter in a given R value, little r value, and a V0, an initial value. And then because the calculator has trouble with separating capital R with little r, I've just written that variable as big R. And big R is calculated as on the previous page, 1 plus R on 100, which is 1.125. And then the template will then generate the associated recurrence rule, and will also give you the direct rule that's based on the same idea. So big R to the power of n times V0. And so in this case, V of n, the direct rule will be V of n, 1.125 to the power of n times the original value V0, which is 100. And so you can also substitute in, I want to know what will the value be after 5 years, and you'll see the answer repeated there. And then if you scroll down a little bit further, you'll see it also will list the first few terms, just so you can see how the progression is occurring. And finally, it also has a solver in it. Now, there's no time really now to go over the construction of this notes page, but in a later webinar, we hope to go through that process. So for example, in here, this value, if I click on it, will show me how the value of little n is being calculated. Okay, so that's pretty much it for problem 1. So let's go back to problem number 2. So we're staying on this planting idea. A slow-growing shrub, seedlings planted, known to grow at a rate of 10% of its current height per year. Its height at the time of planting was 20 centimetres. After how long will this shrub reach a height of 1 metre? On average, how many centimetres of growth does this represent per year? And if the tree grew at a constant amount each year, what annual percentage would this represent? So this question is trying to get you to think about the differences between linear and geometric growth. So we start by just looking at the geometric growth, and then we see what will be the, an equivalent effect for a linear growth pattern. Okay, back to the calculator. So we're now on problem 2. Okay. So I think by now, with a 10% increase per year, it's reasonable for you to see that you could calculate the number of years it's going to take by just saying solve when will the value, that is the height, equal 1 metre or 100 centimetres, keeping it all in the same units. The multiplier is 1.1 because it's 1 and 10 over 100. And the V0 is there as 20, and we're solving it for n. So that's quite a fair amount of time. It's saying that it's going to take nearly 17 years for it to reach a height of 1 metre. Okay, so ignore the next few calculations for a second, and we'll go to the second page. And this is an illustration of the effect and the differences between geometric or linear and geometric growth. So on screen, the red curve is the geometric growth, and you should always associate geometric growth with some sort of curvature. That is, it's not linear. It's not increasing by the same amount for each change in the horizontal axis variable. So I've mirrored here the solution for when does that shrub, which starts planting at 20 centimetres, and its growth rate to get to a height of 100 centimetres. And you can see there that answer, which is about 16.88, is represented by this intersection here. Now, you'll notice here I've put the dots, and then I've got dashes in between. The dashes really aren't used. They're just there to show that there is a pattern, but of course there are no values in between that we would consider when we're strictly using this model. Okay, so just to show that this works, we could say, well, okay, let's say you had a linear thing, you had a linear model, and it did grow by the same amount each year. So not a geometric model, a linear model. What would we do? Well, I guess what we're trying to do is work out the straight line that would allow it to get from 20 centimetres in height to 100 centimetres in height, but maintain this linear shape. So I don't know, hopefully you can see this, but if I click on here, you'll see the rule that's given there, which is the linear rule. V0 plus D, where D is the amount that it changes each year. X is the variable that they've used, but we mean N. And in the other one, you can see that it's a geometric rule. It's our direct rule for a geometric sequence. Okay, so now I'm going to try to change the D value, and I'm going to try to make it so that the blue graph intersects at about that same point, just to give you the idea. Okay, so we increase the gradient to 3, so that 3 means, okay, well, I'm increasing by 3 centimetres a year. That won't be enough. 4 and 5. So if it does it for 5 centimetres a year, if that really did describe the growth, then you'll have reached 100 before the other one. But if I go back to 4, won't quite have reached it. So the answer should be somewhere between 4 and 5 centimetres per year. So let's go back to our story now. And I hope that it's clear that to match that growth, but use a linear model, you'd have to say, I must rise 80 centimetres in 16.88 years, roughly. And that's where the answer 4.73757 comes. So let's say 4.74. If I go back to the graph now and change this and make it 4.74, you can see that it reaches 100 centimetres at the same time, that is about 16.88 years. Okay, and the final question to be answered for problem 2 is to say, well, what percentage change per year, what fixed percentage change, what percentage of the original 20 centimetres does that represent? And so the calculation for that percentage is to say, well, it's 4.7-ish centimetres from the original of 20 centimetres multiplied by 100. So the correct answer is about 23.7%. Okay, so hopefully you're still travelling okay. We'll we'll jump to the next problem. So let's go back to the PowerPoint and look at problem 3. And now we get into the guts of financial applications of this geometric growth, looking at compound interest-based problems. So NAM invests $2,000 in a bank account at a rate of 7% per annum, and a few options available for compounding periods per year. And he hopes to keep the account until it grows to a value of $10,000. So first, how does the number of compounding periods affect the growth of the investment over the 10 years? And B, if the compounding period was monthly, how many years will it take that investment to reach 10,000? So that's the problem that we're going to investigate in problem number 3. So we'll jump to the next one. That sheet is just the spreadsheet that makes the graphs. We'll go to problem 3. And here you can see is entered the most simple calculation where the amount, the period of compounding is annual. So that is the straight application of the geometric rules used previously, where it's 7% per year over 20 years. So that's really just R to the n times V naught. And that says that if you do it over 20 years, you're going to get to about $7,739. However, as we know, sometimes the compounding is not annual, it's monthly. And so the next calculation shows that even though the multiplier previously was 1.07, or 1 plus 7 over 100, that won't be true if you are compounding monthly. You have to divide the 7 by 12 to work out what the compounding multiplier will be on a month basis. And then, of course, you need to work out how many months in total you're talking about over 20 years. And so that's what this part is here. So rather than actually calculate it, just leave it as the product of 12 months a year times 20 years. And so you can see that if you had $2,000, you are really going to make a little bit more money if the compounding is monthly rather than annual. So this process, of course, continues if you did it weekly. You'd get a calculation like that, and there's a little bit more, not too much more, $40 odd. And then you could keep doing that. However, I thought it might be useful to see this calculation, and that's to say, well, in general, if you're compounding it over a different period and you know the number of compounding periods per year, you can just make up a letter or a variable name in this case. CPY is really just an acronym for compounding periods per year. And so the general pattern is it's 1 plus 7 over the number of compounding periods per year. Some people would use the letter K, but I'll just keep it a little bit more intuitive now. And then to that calculation, you'll notice here at the end of the calculation is a vertical line. And that vertical line is for given that. And you can find that here in the control equals, and that will bring up a palette that will allow you to access that. Okay, so, pardon. Okay, so then you can enter in the number of compounding periods a year, but a list of them rather than just one of those. So here I've entered 1, 2, 4, so yearly, half yearly, quarterly, monthly, fortnightly, weekly and daily. And you can see that the values at the end of that time period have been calculated for each of those compounding periods. Okay, and the final thing for problem number 3 is to say, if you did it monthly, how many years would it take for you to reach 10,000? And that's that familiar solving rather than substituting type calculation. And you're really saying, when does V of n equal 10,000? So when does 10,000 equal 1 plus 7 over 12, because we want 12 compounding periods per year. And it gives you the answer approximately 23 years, or just over 23 years. Okay, so that's the end of problem number 3. Let's go to problem number 4 now. And problem number 4 is where we start talking about geometric decay. So up until now, the first 3 problems are examples where the geometric models are used to model growth of something, growth in the height of the plant or growth in the money. But in this case, we are using geometric models, recurrence models, to analyse a situation in which the value is decreasing or decaying, hence the original title. So in this example, Jana purchases a high-end gaming laptop for $3,200 and discovers when she researches that usually the market value of such a thing depreciates by about 24%, excuse me, per year. First question is, what's its value after 3 years? And if she plans to replace it when its value is first less than $500, how long will this take? Okay, so we jump back to the calculator thing and we'll go now to, oh, I didn't show you this. Okay, that was for the previous problem. Again, it's just another template for calculating compound interest and using solving to work out values, the time it will take for the investment to reach a particular value. Okay, we'll keep going. So here's our scenario. Something starts at 3,200, that is the gaming computer value. However, you'll notice in the formula that the R is still there, the big R is still there, but in this case it's being subtracted. So it's 1 minus 24 over 100 rather than any pluses involved. So the thing will decrease in value. You'll notice that after 1 year, that computer is worth 2,432. So that's quite a drop in 1 year. And this is in the nature of this geometric style of change. So the second year, it's about 1,848. And it gets to 1,404. However, if you want to know its value after 3 years, you've got 2 options. You can just use the recursion rule if the number of years that you're calculating for is small, or you could similarly just do a substitute command. And the final thing is to work out when will the value of this computer be 500, and it looks that from the solving command there that at about 6.76 years, or because it's calculated annually, you would be talking about 7 years for it to have got below 500. Okay, so similarly, reducing balance depreciation has its own template. So if you know the annual rate by which it depreciates from its previous value each year, and you know the starting value, you can work out the big R value, the multiplier, and you'll notice now the multiplier is less than 1. And so that's the way of thinking about it. If the multiplier is less than 1 in all the stories that we do, that will mean that there's a decay in the value or a decrease in the value. Okay. This template will also calculate terms and also do the solving for you if you wish. Also for that problem, and we'll just return to the last problem, which is problem 5, where we're comparing investments. And this is a familiar exam style question, exam 2 style question, I guess, where we're looking at someone wanting to invest and being given a few options with different compounding periods and different annual interest rates. So first we'll explore which of those options is going to give her the most over the year. So it's a term deposit account for 1 year, and there are 3 possibilities she has to pick which is going to grow her money the most. And then we'll look at the idea of how effective rates for a nominal or known annual rate of 8%, what is the effective rate and how does that compare to the nominal rate? So back to the calculator. So this is the first scenario, option A, and in option A it's 8% and it's only compounded annually. So we're just looking at 1 year. So we're going to call the number of compounding periods K. And so if it only compounds annually, there's really only one interest calculation that gets added on, and that's the 8% of 2,000 added on. So 8% of 2,000 is 160, and that just gets added on. So you end up at the end of the year with 2,160. However, again, using this given that or substitute command, you could say, well, if this is the rule in general, but the R value was 7.95, so it's a lower percentage rate. So it might seem attractive, but the K value is 4, that is that it compounds every quarter. And the cumulative effect of that after the 4 interest calculations are added to the balance is that you end up with another $3.80, which might not seem a lot, but it's certainly better than the first option. And then the third option is for a lower rate still, but in this case it's compounding monthly, so the K is 12. And so you end up with a little bit more again. So in fact, even though option C has the lowest of all of the rates, it gives you the greatest final value at the end of, and this, remember, this is just for 1 year. Okay, so that raises the question of when you are deciding which is better, you have to factor in the percentage rate annually, the nominal rate, and also the number of compounding periods. And so the final bit of calculation is to say, well, we could use a template to do all of these things and enter in the values for the 3 options, the values of the nominal rates and the K value and the number of years if that's different. So that may be of assistance. But let's get back to effective and nominal rates. So I'm sorry if this is a little bit small to see. I thought it'd be good to get it all on the one screen. So if we return to option A, where it's 8%, and you're talking about $2,000 after a single year, just focusing on a single year, the way to work out the percentage increase between the start and the end of the year is just to say, well, okay, what is the value at the end of that year? And then say, well, so you'll see here this calculation says, find the value at the end of that year, take away the original 2,000 and divide by the original amount and multiply it by 100, and that will calculate the percentage change, which unsurprisingly is 8. However, if you compound more frequently, your money grows. So in these scenarios, it's still 8% per annum. it's still 2000, but the compounding is happening more frequently. So in each of these cases, such as the second one, when K is 4, the percentage change is 8.243. This continues till you get to the last one, where if it was possible, it was compounded daily, and that is effectively 8.328% increase on the original amount. And so that is where the effective idea comes from. The effective percentage rate, it's really like saying, in the context of the story, what does it mean? It's the equivalent nominal rate that would account for these shorter compounding periods. So it allows you to make better comparisons. So I hope that that was helpful for you. That's the end of this webinar. There is a student worksheet separate to the tutorial which was done today, which gives you some further questions to practice the skills and practice using the calculator in order to solve the problem. So thank you very much, and I'll see you next time when we look at the TVM solver.